All right, hello and welcome back, everyone. Today we'll be talking about spectra, and I will introduce basic stable homotopy theory to you. So, yeah, without any further delay, let's get started. So, recall how we define uh, recall how we define normal homotopy groups for topological spaces. I mean, you'll quickly realize the limitations here and why we need to do more or why we need to modify topological spaces. So your nth to a homotopy groups is defined to be you look at all the maps from pointed sphere to pointed topological space and take their homotopy classes. That's all. So yeah, this is how you define homotopy groups. The operation here is that instead of pinching circles, you pinch spheres. And yeah, the question is how do you compute? And it turns out to be a very strong topological invariant, etc., etc. The question is how do you compute them? So before I mention how do you compute homotopy groups, let's see how we compute our usual homology groups. For that, we use something called as homotopy pushout. This may not be exactly the version that you have seen in the basic algebraic topology course, but trust me, this one thing captures all the information about long exact sequences that you get out of that you get out of homology theory and cohomology theory. And that one thing is your homotopy pushout. What do I mean by that homotopy pushout? But before mentioning that, let's see how pushouts behave with respect to homotopy theory. So look at this diagram, S1 to D2, D2. Can anybody mention what is the actual push out of this diagram? I would like to mention.
I have no idea. Yeah, you can say no.
Yeah, so
How about the two sphere?
yeah, that's two sphere, right? It's disk.
Oh,
Yeah,
yeah.
boundary of the disk is circle. Attaching two disk with at their boundary gives you the two sphere. That's two sphere. This is your push out. Now you apply homotopy on the D2 and D2. They're contractible, right? So that's a point. This is also a point. Attaching two points along anything will give you a point, right? So there you go. Your D2 is homotopic to the point. S1 is exactly S1 on these two corners, but on the push out corner over here, as you can see, let me highlight it. S2 is not homotopic to your your point. Now that's a problem. That means that your actual pushouts do not respect homotopy. But we can do something here that will make it respect homotopy. So instead of taking the actual pushout of the diagram, we replace them by mapping cylinders. What do I mean by that? Now let's get back to this diagram. Let's keep it this way. Now let's apply something on this diagram. That is, instead of looking at the push out of S1 to this point star, take the mapping, take the mapping cylinder of this map, this F. That will be a cone, just a cone, right? S1 cross I, top portion is identified with the point. That is your S1. Now, if you take the push out, it will give you. Now, the thing that you got here, this is homotopic to your two sphere. So, even though push out do not respect homotopy, if you replace them by mapping cylinders and then take the push out, that does respect homotopy. This is called co-fiber replacement. It's true for arbitrary model categories, and this is how you define homotopy pushouts. Now, why talk about them? Now, yeah, let me define the homotopy pushout now based on that. So I will denote in my talk homotopy pushouts by this symbol H on the corner of the pushout just for this talk. How do I define this? This is defined to be pushout of the co-fiber replacement on the corner. There you go. Now it's a easy or I mean, yeah, it's just an exercise for you to check. Even if I do not replace both the corners, if I replace any of the corner, still it will give me the same thing. Exercise replacing one of the corner is good enough. Extremely easy to see for topological spaces, true for arbitrary model categories as well. Now, why talk about them while computing homology groups? Because if I have a homotopy pushout square, we get a Meyer-Vittori sequence of homology or cohomology. So it's very easy to see. You just have to read the diagram in this angle. So you start with your H I of A, Hi of B, direct sum of Hi of C, direct sum to Hi of D, to Hi minus 1 of A, so on and so forth. My arbitrary sequence. Same, this is also true for cohomologies as well. If I have a homotopy push-out sequence, I'll get a long exact sequence of Mann-Vittori. Cool, right? So homotopy pushouts captures the long exact sequence of homology. Now, what about homotopy? For that, we need to introduce something called as homotopy pullback square. So that is literally dual version of homotopy pushouts. So you define the homotopy pushout pullbacks like this: A, B, C, D. So instead of replacing them by co-fiber replacements, you do the fiber replacements. This is defined to be, yeah, this is defined to be PG. This is your vibration, B, PF, and then you take their pullbacks. This is your PF times B, PG. What is this PF? This is the path space vibration. This is all your paths um in yeah in B power I in all the paths in B that start at X. Start at the image of F. Okay. And if I have a homotopy pullback square, then I get my long exact sequence of Meyer-Vittori in terms of homotopy groups. Again, read it like this. So you start with pi I of D to pi I of A, direct sum of pi I of C to pi I of B to pi I minus 1 of D, so on and so forth. Yeah, this is a pullback here. Yeah. So far, so good. Are we following? Cool.
Yeah.
Now, there are two explicit type of homotopy pushout and homotopy pullbacks we will particularly care about or will be in our interest, and those are called co-fiber sequence and fiber sequences. And those are more familiar to you. So a co-fiber sequence is a pushout. So right, one of the corner is pointed. That's it. Then A, B, C is called a homotopy co-fiber sequence. Note that if I have a homotopy cofiber sequence in terms of homology, I will get a long exact sequence by default. HIA, HIB, HIC, then HI minus 1A, and so on and so forth, right? This is your long exact sequence with respect to, the which axiom is it? Was it the exactness axiom or something like that? If I have something like this, AXX by A, this will induce a long exact sequence in homology. This is exactly that. This is exactly that. This, whatever this means to you, one step generalization, another way of phrasing that statement is this guy. That's all. So this information is nothing special. It's coming from the homotopy pushout. What is a homotopy fiber sequence? Yeah, what is that? So you are pinching again one of the corners. So A, B, C, and take the pullback of that. Then A, B, C is your homotopy fiber sequence. And guess what? If you have seen this theorem that or this fact that a fibration sequence or a fiber bundle induces a long exact sequence in terms of homotopy groups, this is exactly that information. Your F, the fiber bundle FEB, induces a long exact sequence in homotopy groups. This is that information. Whatever this means to you, this means the same thing. So this is basically introducing these new tools so that you can get used to it, and new tools, but has a similar old flavor. That's all. Now, why am I talking about this? Because these things. So last time Colton talked about triangles, right? Triangle, distinguished triangles. Talked about uh, triangulated categories. This objects, these ABC, these ABC. By the way, this is so if I have a okay, let's not like speed up. So these things they behave like a triangle almost. What do I mean by that? If we start with a map, oh, I don't have much space. Let's see if I can squeeze it here. If I start with a map A to B, squeeze it, F, I can always extend it by taking its push out, right? Homotopy push out. Call this CF. So A, B, CF. That's your cofiber sequence. And I can keep doing it. And if I do it one more time, if I pinch it, pinch this side on the top. Now here is the thing. You guys know about the pasting lemma of the pushouts? Yeah? You guys know about the pasting lemma of the pushout? It's an exercise for you to prove that pasting lemma of the homotopy pushouts also holds, and pasting lemma for the homotopy pullbacks also holds. Okay. So homotopy pushout of of this guy, homotopy pushout of this guy is the homotopy pushout of this guy, right? A star star. And what is that? Suspension on A. Right? Now this looks like a distinguished triangle. Also, if you apply suspension one more time, um, you'll get something like this: BCF suspension A to suspension B. There will be a minus sign here, and yeah, I'm not mentioning this, but yeah, I don't want to write this. So if I start with a commutative diagram X Y A B, you can always push it. Okay, let's write down that. If I have a commutative square like that, you can always extend this XY to CF. to suspension of A. This is your A, this is your B, this is your, I don't know, F, G, C, G, suspension of B. And you can fill in this diagram like this. So the problem is, it looks like a triangle, but this is not a triangle because you can't shift back. Suspension and loop, these are adjunct, not inverses. At least not for topological spaces. So you will get a sequence. So if you take the pullback, if I start with okay, let me erase the what we want for now. So if you start with the map A to B F, right? And similarly, you can fit it in a different triangle, that is your FF, by taking the homotopy pullback to A to B. But this guy is not this is a shifted towards the left side, right? But this is not coming from the coming from as the inverse of the suspension. So in other words, suspension or loop are not automorphism.
So I just wondering, I missed last lecture last time. So in the definition of derived category, do you want the suspension always to be automorphism?
Yeah, this is the shift functor, and shift functor is the automorphism in the category, right? So you always want the suspension here is the shift functor.
Mm.
So that's a problem, right? This is the problem. This is the problem over what you are saying. So what do we really want that I erased over here is that co-fiber and fiber sequences to coincide. Let's zoom out for a while and let's like summarize what we have done so far, because this is the most important part, to coincide. So if yeah, sorry, what you really want is that our homotopy co-fiber and the fiber sequences to coincide. In a broad sense, we want our homotopy pushouts and pullbacks to coincide. If that happens, then we can compute our homotopy groups out of a homotopy pushout square. So far, we can just use the homotopy pullback square, but in computation of the I don't know homology groups of some manifold, what we have seen, we tend to break the manifold into smaller pieces and glue them in a fancy way, and compute the homology groups in that way, right? By computing the homology groups of the smaller pieces. For homotopy groups, we can't do that. We will be able to do that if we get to use the uh, long exact sequence from the push out. So the upshot of this discussion is that what we want our homotopy push out and pullback square to coincide, and they do coincide modulo some obstructions. Let's look at that, and that is called your Blaker's-Massey excision theorem. Let me introduce that. Um, okay, yeah. So before that, like a map is called M connected, A to B is called M connected. Okay, call this map F. Call this M connected. If your homotopy groups are induced homotopy groups are isomorphic for I less than equal to M minus 1 and AP for I equals to M, then the map is called M connected. So your homotopy groups are same basically up to M minus 1 level. So what does Blaker-Massey excision tell you? If you start with, let me erase this. If you start with a diagram QAB and take its homotopy push out, yeah, P is your homotopy push out, okay? And then you take the pullback of this diagram. homotopy pullback of this diagram. That let's denote this by QR AB is a homotopy pullback. So you have a universal map over here. I want this to be inducing isomorphism on homotopy groups. It does up to some connectivity. So if Q2A is M connected and this guy, this is a homotopy pullback, and this Q2B is N connected, then this guy is M plus N minus 1 connected. So you can call this a homotopy push-pull square up to M plus N minus 2 level. So a homotopy push out slash pullback coincide up to some level, up to some connectivity level. That means whatever discussion we just had in the last slide, that will be holding true, but up to some connectivity level. So what we really want right now is to get rid of the connectivity. Are you following so far? Like what you want to do? Yeah. How we'll do it, we'll get that later, but this is what we really want. We want to get rid of this connectivity. That is the only obstruction here. So to do that, let's make a few observations now. So, um, yeah, let's see. Yeah. If this map A to B, yeah, observe this. If a map A to B is M connected, then what happens to their loop spaces? Let's look at that. So what is your pi I of omega A? Now you can use your loop suspension adjunction to see that pi I of omega A, that is your homotopy classes of map A psi to omega A. And by loop suspension adjunction, this is isomorphic to your Si plus 1 to A, that is precisely your pi I plus 1 of A. Similarly, this is your pi I plus 1 of B. Now, I know that pi I plus 1 of A to pi I plus 1 of B, this map is iso for I plus 1 less than or equal to M minus 1. That means that this guy is iso for I less than or equal to, less than or equal to M minus 2. Meaning that my connectivity is decreasing. So this is a minus 1 connected. So looping decreases connectivity, but we want the opposite, right? To increase the connectivity. So for that, you need to deloop it. That's all. So yeah, let's say, so for that, we need to deloop it. So if this guy is A to B2 is 8, there's a reason I call this A2B2. We'll see this. So if this guy is N connected, and I say that, I assume that if there exists a A1 for which your loop space of omega A1 is your A2. So that means that A2 is being delooped. And loop space of omega B2 is, call it B1. Then your A1 to B1 will be N plus 1 connected. Delooping increases connectivity. And this is exactly what I want. I want this QA, this map from Q to A, and this map to be Q to B to be highly connected. So that I can use this homotopy push out square as pullback square for higher and higher levels, right? This is what we exactly want. So that means that we need to keep track of, we need to keep track of all these deloopings. So this is where we introduce a collection of the spaces where the next space is the d-loop of the previous space, loop space of the previous space, sorry, loop space of the previous space. So infinite d-looping of a base space exists. That's exactly what you're doing. We are trying to increase this M connectivity. We are de-looping, we are looking at spaces like that for which this infinite de-looping exists. So this space is, these maps are infinitely connected somehow. Does it make sense so far? So this is what we are doing. So we are starting with a base space x0, and um, our next space x1, that is the de-looping of the space x0. That means that loop space of, oh, I did not write this down. That means the loop space of omega x1 is x0, and so on and so forth. Loop space of x2 is x1. Loop space of x2, x3 is x2. And this is exactly what we want. Now, if I use this infinite d loops, if I use these spaces like that in our diagram, in our Blaker-Smith excision, we are happy now. I can use this as a push out and pull back square. And this is exactly what is called a omega spectra. So using a omega spectra gets the job done. And that begs the question, what is a spectra? So I introduce omega spectra without introducing spectra, but I'm going to do it soon. So yeah, before I do, are there any questions so far? Because now we are going to switch gears.
So if you start with x0, there's no guarantee the omega spectrum always exists, right? It must be some condition.
No, no, no. Yeah. I mean, we are trying to build this infinitely d-looped spaces. I'm not saying that you start with x0. You look at the space x0 and try to find a space x1, which is looping, that will give you x0. And this is not a easy process. This is a very hard process, honestly.
Mm.
So how hard you ask, how important you ask, so much so that people like, you know, Peter May had to introduce operates
Mm.
to find this infinite loop spaces. These are called infinite loop space machines back in those days in 1972's operates, um, gamma spaces as well.
Yeah.
Yeah, you're right. Finding these spaces is hard. That is true.
Mm.
Finding this infinite loop space is really hard. There is an example that is easy. That is your Eilenberg-Maclaurin spaces, and that is the easiest one that I can think of. But yeah, building these spaces is hard.
No, if
So
you simply deloop it, I think that really works.
what do you mean by simply de-loop it?
Suspension.
But from, yeah, from x0 to, you can go to suspension of x0, but you don't know the loop space of suspension of x0 if it is same as x0, right?
No, wait, let me see.
What you said is true. That will give you a suspension spectra, but that's not your omega
no, I
spectra.
do not mean suspension spectra. I do mean what I mean. So,
Uh-huh.
by looping it, you have um, hmm, maybe that's an option in some category, yes, but not true in they might be true in general or something. So if this is simply connected space
Uh-huh.
and we are in the rational category, then it's true. At least we know this. For the other thing, yeah, I mean, I need to think about a bit, but D loop is well, if you enlarge the category, maybe that's also true.
Okay.
So I think there should be some. some candidates that we could do for the delooping construction.
Okay, I'd like to see them. Yeah, definitely. Yeah. I mean, what examples I have in my mind, they're very basics. So, yeah. All right. Yeah, let's move on. So, that's your omega spectra. Yeah. Yeah. Now note that I want to define a spectra, and that will actually pop from this discussion. Um, this if I have a map from if x0 is weakly equivalent to omega x1, that means that I have a map in this direction x0 to loop space omega x1, right? That means that I have a map by loop suspension at a junction suspension of x0 to x1, and I want to capture all this information. So instead of saying that this guy is a weak equivalent, instead of saying this xi is weak equivalent to your loop space of xi plus 1, I want to say something like this. It is a map from loop suspension of xi to xi plus 1. And that will give you the definition of spectra. So let's define it. So your spectra, yeah. So your spectra X is collection of spaces. It's a topological spectrum. There are different ways, I mean, broader way we can define spectrum, but right now we are just talking about spectrum of topological spaces. Collection of spaces, x0, and they are connective spectrum. So that means that you can also run it from on the Z indexing, but I'm running on the N indexing. So x0, x1, x2, so on and so forth, such that collection of spaces and the collection of maps. Uh, uh, yeah, suspension of x0 to this for the matrix I plus 1 called the map sigma I. Um, yeah, do I want something more? No, I don't think, I think this is good. Yeah, a spectra is a collection of all the spaces and all these maps. These are called, I think, connecting homomorphism or something like that. Yeah. A map between two spectra is a spectra. This is a definition. A map between two spectra if such that x to y is something is a collection x0 to x1 to x2, and this is your y0 y1. So the map F will be induced on all the topological spaces such that this diagram commutes with respect to their suspension. So what this actually by this diagram, what I'm actually writing down is this diagram. Suspension of xi to xi plus 1, suspension of yi plus 1, this is your fi plus 1, this is your suspension of fi, and they commute. Sorry, this is your sigma I as well. So that is your spectrum, this is your suspension, this is your map between two spectrum. And let's first introduce all the tools that we need. Homotopy push out of spectrum. Again, the idea is to define them on the on the space level, and make sure they commute with the structure. Oh, I remember what they call these are called structure maps. Yes, structure maps. They commute with the structure maps. That's all. That's the idea. So a homotopy push out of the spectra XYZ W, a homotopy push out must have this information, right? Xn2, Yn2, Zn2, Wn. This information, all of them has to be homotopy pushouts such that they respect the this connecting maps. So what does that mean? That means that I have also xn plus 1, yn plus 1, zn plus 1, wn plus 1, and I guess this will be hard to write. This is your suspension of xn, this is your suspension of yn, this is your suspension of Zn, this is your suspension of Wn. Yeah, I want this square to be commutative. Let me think. Is that what I want? Yeah, I think so. Yeah, I think so. I'm a little bit fumbling, but yeah, I want this square to be commutative. Let's just accept it for now. This square to commute. Similarly, you can define homotopy pullbacks. Yeah, and you can also define these things: the wedge of spectra and product of two spectra. How do you define them? You define them level wise. So xyz, your level at the nth level, this is your xn, which yn. So is your product spectra xn product with yn. And here the structure maps are natural to follow. So if you have the map suspension of x which y of n, that is your suspension of xn which yn, that is your smashing with s1. Let's use that. And smash product, distribute over the wedge. So s1 xn which s1 which yn. This guy will give the map to xn plus 1. This guy will give the map to yn plus 1. This is your wedge. And together it will give you the sigma n, the structure map. Yeah. Something similar you can do over the product as well. There is only one thing that I'm not going to define, and that is your smash product. X mass Y. Now, why I'm not going to define it? Because to define this, we need to involve some choices. And these choices do not matter when you talk about its homotopy category. These choices will all be equivalent. But when we talk about an actual smash product on actual spectra, these choices will matter, and these are called handicrafted smash product. Yeah. So I'm not going to talk about that. Just know that smash product there is a way of defining smash product, or for you a tensor on spectra. There is a way to define it. You can talk about it in the end if we have time, but not now. Let's talk about a few quick examples, and then we can talk about its homotopy category. The first example is your Eilenberg-Maclaurin spectra. We all know about Eilenberg-Maclaurin spaces, K-I-K-A-N, right? The ith homotopy group is your, nth homotopy group is your A, and rest of the homotopy groups are 0, right? Now, if you look at its loop space, if you look at its loop space, this is your pi I plus 1 k a comma n, and that means that this is your A when I plus 1 equals to n, or I equals n minus 1 and 0 elsewhere. What is this? This is your Eilenberg-Maclaurin space, but now with rank n minus 1. Right? And this is exactly the omega spectrum. So loop space of K A comma n is your K A comma n minus 1. It is denoted by HA, the Eilenberg-Maclaurin spectrum. We know by Brown's representability that your singular reduced cohomologies are homotopy classes of these maps into the Eilenberg-Maclaurin spectra, right? You have seen something like this. In fact, all your cohomology theories are some omega spectra. That's the first time when you introduce spectra while studying K theory. So all your spectra that that you see in a topological K theory course, such as your Thom spectra, the AMO spectra, AMU spectra, um, and the K theory, the complex K theory spectra. All of they are examples. The other example is your suspension spectra that you briefly mentioned. That is your, for example, it's a sphere spectra. So your S0, S1, S2, so on and so forth. Note that here connecting maps are structure maps are your actual isomorphisms. So suspension of S0 is literally isomorphic to S1. Suspension of S1 is isomorphic to your S2, so on and so forth. These are called suspension spectra. And yeah, I think so far we are good with this many examples. We are good with this many examples. We don't need any more example, at least for this introduction to spectra. Now we want to give a model category structure. We're going to do homotopy theory on this guy, on this spectra, because we'll quickly see they are very nice. Now to do that, we need to give it a sense of weak equivalence, right? And it turns out there are three candidates for it. The first candidate, three notions of equivalence in spectrum. Your first candidate is okay. Let's start with this candidate homotopy equivalence first. I'm switching my notes. So a map, X is your spectra, Y is your spectra. They are called homotopy equivalent if I have a map from F to a map F, and a map in G such that G compose F is homotopic to your identity, and F compose G is your homotopic to your identity. Now, what is this notion of homotopy? For that, I have to spend some more time talking about that, smashing thing, but don't worry about that for now. It means a map from, let's say, homotopy, right? So x smash I plus 2y. This is your notion of homotopy in this category, but let's not worry about that. Just know that there is a notion of homotopy, and we can define homotopy equivalence. The second way of doing that is level equivalence. That will be more familiar with you guys or with this discussion. So I call that a map between spectra x to y f is level-wise equivalence. It's a level equivalence if on each of the space level they are weak homotopy equivalence. These are weak homotopy equivalence. Okay, for all n. So level-wise, my homotopy groups are same. The third one is the one that will be of interest to us, is the stable equivalence. For that, I need to define the stable homotopy groups. So stable homotopy groups of a spectra, these are basically the homotopy groups of a spectra, is that we look at the homotopy groups of all on the space level and take their colimit. So you start with your pi k of x0, then pi k plus 1 of x1, pi k plus dot pi k plus n of xn, and take this colimit. This is called stable homotopy group or homotopy group of spectra. And I say that your x to y, this is the notion of homotopy in spectra. So I say that a map between spectra x to y is stable equivalent if it induces isomorphism on all the stable homotopy groups. Okay, so it's literally like the equivalent notion of weak equivalence for our actual homotopy groups. Turns out you can give model structure on this level equivalence and both stable equivalence. The homotopy equivalence is a little too strong for choosing them to be a weak equivalence, but you can choose both of them. For today, I will show you what is the stable model structure on spectra using the stable equivalence, because this is more close to me. This is more close to me. This level-wise equivalence also give you a model structure. This is called a strict model structure, but I will not talk about that today. So yeah, before talking about that, now let's retrieve all the features that were promised in the beginning of the talk. Like this fits into that, the suspension map fits in the triangle, suspension and loop, should be act like, inverses to each other. All those caveats that we started in the talk with, all of them getting fulfilled if we replace our space by spectra. All of them, your homotopy push out and pullback square coincide. So let's do that one by one. Yeah. Yeah. Um, Taking a break. We've seen a long talk. So
do you want to mention actually why it's called stable?
why it's called stable? You mean
I mean the suspension theorem in homotopy theory.
oh, you mean
Prudential.
Prudential
Prudential,
suspension?
yes. That's really where it comes from.
Yeah. It comes from there actually. And for this talk, I did not prepare that.
Okay, no problem, no problem. Yeah, just
But
out of curiosity. And by the way, when you
yes.
finish it, I know what I'm talking about by delooping. I really know what I'm. There is
Okay,
such a
okay,
thing.
okay.
There is such a thing. Just go ahead. I do not want to interpret here, but when you finish it, then we can discuss it.
Yeah. Now that Guanu,
Sorry, can you repeat that again? Why it's called a stable equivalence?
Oh,
I'm going to talk about that. Yeah.
yeah, you okay? Very nice. You're going to do that.
Yeah. Now that you mentioned it, now I'm going to talk about that. Yeah.
Okay, sure.
So this stable equivalence, I give you the like the predefined product, but let me give you the motivation now, as Guanu has mentioned. So in topological spaces, we have something called as Freudenthal suspension theorem. Yeah. This theorem actually motivates all this theory, all these stable homotopy groups. So what does it tell you? That tells you that if you, okay, let's start with sphere, for example. Yeah, your um one sphere. You take suspension of this guy, you will get two sphere, right? You keep taking suspension, yeah, you will get three sphere and so on and so forth. Now, what it tells you after taking enough suspensions, your homotopy groups will stabilize. That's all it says. So your homotopy groups will not change after enough suspensions. I can't recall exact theorem at the top of my head right now, but it says something like this. If I start with a map x2 yf, and yeah, that map is, yeah, no, I can't recall it right now. I'm sorry. If you can recall Guanu, I would like you to recall it, but yeah, that essentially tells you this. Like after taking enough suspension, your homotopy groups will stabilize. And that homotopy group is called stable homotopy group of sphere. In particular, this is true for in particular, but this is true for all CW complexes.
There is an even more explicit way to see this thing. So if you can draw the diagram, the table, like on the diagonal, it eventually is actually stable, and why it's I think it's the very original reason why it's called stable.
Yeah, for spheres, yeah,
Yeah, for any space, in fact,
oh, for any space, the
for
diagonal.
any space, the
What do you mean
diagonal.
by
But
diagonal?
we only compute the spheres, and we care about the spheres, in fact.
Yeah. Okay. Yeah, let's move on. Let me finish what I want to say for now. We'll talk about this later. So, okay, let me promise you what I started in the beginning, that suspension and loop are inverses to each other. Let's first show you that. So suspension and loop, these are inverses in spectra. Up to stable equivalence. Up to stable equivalence. What do I mean by that? That your pi I of x, I'm still written k here, pi k of x is isomorphic to your pi k plus 1 of suspension of x. That is same as isomorphic to your pi k minus 1 of loop space of x. Okay. Now to see this is literally using the basic property of the colimit. To see this, let's unfold the definition piece by piece. So what is your pi k of x? Your pi k of x is colimit of these guys. of xn, then pi k plus n plus 1 of suspension of xn, then pi k plus n plus 1 of xn plus 1, so on and so forth. That's your pi k of x. And your pi k of suspension of x is this guy. Pi k plus 1 of suspension of x is this guy. Whole limit of n to pi k plus n of pi k plus n k plus 1 plus n of suspension of xn, then pi k plus, give me 1 second, pi k plus 1, oh, it's fine, plus n plus 1 of suspension of xn to pi k plus 1 plus n plus 1 suspension of xn plus 1, so on and so forth. Now I want to show that these two colimits are equivalent. That means that if I focus on a subsequence of a colimit, a subsequence of this index category that is also a cofinal subsequence, and then take its colimit, will still be done, right? All you have to do is find that cofinal subsequence indexing. So what is that indexing? So I will make sure that this guy matches with this guy somehow. I on these two indexing. So for that, what they have done here is that take the colimit of instead of n, you take the colimit of, focus on these terms, k plus 2n x2n to k by k plus 2n plus 1 suspension of x2n, and so on and so forth, and focus on this guy. And here, actually, I don't need to do this. I don't need to do this. Never mind. Never mind. Never mind. But if okay, give me 1 second. Let me make sure that I'm not tripping. And here, if I apply the suspension k plus n plus 2 suspension of xn plus 1. I see. Here, yeah. So forget about that. Just focus on what I was gonna say. Focus on terms like these over here, then over here, over here, over here. If you look at this subsequence, if you plug them out, these guys out, and then take the colimit, it will still end up in the same colimit, right? And that means that these two coincide. That's all. So colimit of this guy is same as the colimit of the YOLO portion. And the YOLO portion, and that these two YOLO portions are same, so that means that these two are same. Question? If this seems weird to you, let me know. Does it seem fine? Anyone? I want to know yes or no, like from anyone. If it's no, then I will repeat again.
I'm good.
Okay. Okay. So similarly, you can do for the loop spaces, the loop space version over here. In fact, for the loop spaces, it's very easy to see, right? Because your from the loop suspension adjunction is pretty easy to move from loop to suspension. So it's nothing much fancy on the second part. Second part. So yeah, for the loop space, it's also true. That means that your suspension and loops are adjunct here. Um, The second thing I want to do as a corollary of this guy is that these three things are equivalent. That is your if x to y, this is your map f. This guy is stable equivalence if and only if your suspension x to suspension y is stable equivalence if and only if your loop x to loop y is a stable equivalence. How do you see how do you see that? So that's nothing but extending that theorem over there. So pi n x, this is your isomorphic to your pi n minus 1 of loop space of x. This is your isomorphic to your pi n plus 1 of suspension x. This is your pi n plus 1 of suspension y, pi n of y, the induced map from F. So if if any of them are, isomorphism, then rest of them will be isomorphism as well. From this diagram, it will drop. Okay. Uh, as another corollary, this is your first corollary. As another corollary, you get that your loop suspension adjunctions, the adjunctions inequalities are also your adjunction unitals are also your unit and co-unit are also your stable equivalence. So x2 over here, uh, suspension of two forward. This is the unit. This is the co-unit and this is the unit. Um, are also stable equivalence. You see this, right? This is true. Let's do that for the at least one of them. So pi k of x is isomorphic to your pi k plus 1 of suspension x. This is what we proved. This is same as saying isomorphic to you after you apply the loop here. Pi k of loop of suspension of x. And so on and so forth. Another corollary is your homotopy. This is the corollary that you wanted. Your homotopy fiber and co-fiber sequence coincide. Do you want to see the proof or do you want me to skip it? What do you want?
I don't know the proof. Maybe you can show at least for co-fiber. Right?
They coincide, so it doesn't matter. Like if I show you one, I'm showing you everything. So I personally like to start with the co-fiber sequence. So let's do it. Since one of Professor Wong has said it, let's do it. It's a fun proof. This is this is using your pasting lemma again and again using the universal property of homotopy pushouts. This is where the homotopy pushout will shine. Equivalently homotopy pullbacks as well. So x, y, Z, this is your F, this is your G. Let's start with a co-fiber sequence, then we'll show that it's a fiber sequence, okay? And all the steps are equivalent. So let it be a co-fiber sequence. What does that mean? That means it fits in a push-out square. It's your homotopy push-out square, right? That, yeah, let me check for one thing. Yeah. Um, okay. Yeah, I have done it over here in a, okay, let's keep doing it, yeah, okay. So that means that this fits in a homotopy push-out square. That means that this Z is stably equivalent to your CY union CX uh, union YX. So I'm taking the co-fiber replacement one. I can take co-fiber replacement on one of the corners. I'm choosing the star corner here. So mapping cylinder over this guy is your cone, right? That's your CX. So these two things are equivalent. Cool. Now I can take homotopy push out of this entire guy. What did you get? You will get suspension of X again by pasting lemma of homotopy pushouts. That means that this guy over here uh, is stably equivalent to by homotopy push out is this guy CY union CY. By looking at this push out, this is where you're getting this guy, and for the uh, YOLO guy, you're getting this guy. Again, I'm taking the co-fiber replacement for this piece. Are you good with this so far? How are you getting these pieces? Yeah, the water push out. If not, let me know.
I'm good to go.
Professor Wang, are you good to go?
Yeah, I'm good to go.
Okay, let's go. Now, okay, these are all the pieces here. Now let's talk about the now I have to make sure these pieces fit into the in your homotopy pullback square somehow, right? So now we have to introduce the homotopy pullback. So let's look at the homotopy pullback of this guy, YZ. So I want to show that this is also a fiber sequence. That means that I have to take the homotopy pullback of this guy. And I'm taking the fiber replacement over here to get this guy. Y cross PZ Z. And note that this Z is also coming from the homotopy push out of of this square. If you ignore this portion, just focus on this guy. This is equality, not isomorphism, literally equality. This is the homotopy push out. by the co-fiber sequence part. Now I can take the homotopy. This is your homotopy push out, keep mentioning it. Now let's take the homotopy push out of this guy. If you take the homotopy push out of this guy, that will give you suspension of y cross z pz, right? And that is same as saying, okay, let me, oh god, so many different colors. The homotopy push out of this guy is this guy. Now, homotopy push out, this is same as by pasting lemma as this guy. Now, what is this guy? This is stably equivalent to your cy z attached at y. Now, what is that guy? By this, yeah, no, let's use this color. Let's use, oh, no, first let's use this. That is your this color. That is same as saying this is, these two are same. That means that your suspension of x is stably equivalent to your suspension of y, z, pz. The homotopy could pull back over here. And by now, since now you can, this is the feature of stable categories. If I have a suspension, I can desuspend it. So that means that your x is isomorphic to your y cross z pz by this corollary that we have seen. So it's seen here. These three conditions are equivalent. That means that this x fits into this this homotopy pullback square, and that means that, so these are all even only if condition, by the way, if you keep track of all this process. So that means that this is your x to y to z, it's a fiber sequence. Are you guys happy with the proof?
Yeah, thanks.
Yeah. This is using, you see the proof, right? We are using the pasting lemma of the pushouts and pullbacks. Nothing fancy here so far. So, I mean, nothing I mean, the only feature that is honestly been used is this feature over here, that you can shift back. That's all. Now, if I have this, then I have something more. This is the next part of this corollary. So many corollaries, just proving that suspension and loop. I actually this. Look at how many data we have skews. All of this corollary, and it keeps on going. Your homotopy push out and pullbacks coincide. So all the promises that had been made in the beginning of the talk, all of them are true. How do you see that this is easy? This is literally your pasting lemma, like just once. So your A to B to C to D. Yeah, this is your homotopy push out. Okay. Note this. Yeah, this is the thing. Note this. This is the homotopy push out if and only if their induced map, um, call this map F. Their induced no, don't call this map F. Call this map F and call this map G. Their induced map on the homotopy cofibers. This is a stable equivalence. This is literally your pasting them of the push out. Let's just do it quickly. So A to B, this is your C, this is D, this is F. This is your homotopy push out, and I can extend it. If I extend it, if I focus on the homotopy push out of the outer square, oh no, outer square over here and here, you get the co-fiber sequence CF. Okay, and if I focus on the homotopy push out of this, of this square, you get CG. Oops, sorry, I'm sorry about that. And these two are stably equivalent by your pasting lemma of the pushouts. Good. So it's a push out. It's a push out square if and only if your um how do I state it? Your A B C F this square C D C G so G. I can extend this square like this, and this guy is a stable equivalence. That's a if and only if condition. That means that this ABCF now do the similar thing for the homotopy pullback. So this is a homotopy pullback if and only if I can extend the square back. Now, now ABCF, this guy, this is a co-fiber sequence. That means that ABCF is also a fiber sequence. ABCF, it's a fiber sequence. So is this guy by the previous theorem we just did. So is this guy. And yeah, it's oh, wait, I think I messed up here. Yeah, I think I messed up here. I mean, the data pieces are in the right pieces, but the flow of the information is a little bit wrong. So this part is true CFCG, and I can state something similar. Homotopy fullback if and only if, if f is stably equivalent to fg. Now using if and only if, using these two information, I want to show that homotopy pushout and pullbacks, they coincide. How do I show that? Let's see. So you start with a homotopy pushout square. A, B, C, D, and got it. It's yep. So this is your CF is isotopic to CG same. So this is the same thing. So this guy A B C F, this entire thing, this A B C F, this is a homotopy co-fiber sequence. Ignoring the D, this is your homotopy co-fiber sequence. That means that this A B C F, this is also a homotopy fiber sequence. Homotopy co-fiber sequence. That means that this is a fiber sequence. That means that this guy is a pullback. And also, I know this guy is a pullback by the same logic, because CD and to CG, these two are, this is also a, this is also a homotopy co-fiber sequence, so it's also a fiber sequence. So I know this guy is a pullback. Now you can use the pasting lemma of the pullbacks to say that this smaller square is a pullback. This square is a pullback. Are you with me? Or lost it?
Yeah, I'm good. Yeah.
Oh, okay. Thank you. Thank you so much. Thank you so much for following. The next feature I want to show, I will take 2 or 3 more minutes and then I will be done. That's it. Actually, 4 more minutes, 4 or 5 more minutes, then I'll be done. The next feature is that the spectra is your additive category. But these are all the signature features of the spectra. when somebody says that spectra, these are the features that should click your mind. That suspension and loop are inverses to each other. Homotopy push out and pullback square coincide, or everything behave nicely. That's all. And you get your long exact sequence of stable homotopy groups of spectra. Either of the squares doesn't matter. So these are the signature feature of the spectra. In fact, you can collect all these features and give them a, call them a stable model category where um, features are these features are retained. So these are the signature features, and the next property of the spectra is that spectra is additive, meaning that your co-product and co-product coincide. So on the space level, I have this inclusion xn to xn cross yn. I want to prove this x cross y to x cross y. Your product and co-product coincide in spectra. Yeah. How do you show that? So for that, you let me see your um pi k of x which x which y is same as is isomorphic to your pi k of x um uh, direct sum your pi k of y and pi k of x cross y is isomorphic to your pi k of x cross pi k of y, right? Now, let me see what I have done here. Yeah. Now, these two are, give me one second. Now, um, what do I want here? Okay, this is isomorphic, we know. Yeah, this is isomorphic, we know. These are abelian groups, so product and co-product will coincide. This is isomorphic because pi case they respect the product structure, homology groups respect the product structure. So these two we know. This is what I don't know. Yes, this is what you want to prove. That pi k of x which y they coincide with pi k of x pi k of x direct sum with pi k of y, and for that we need to resort to Meyer-Vittori sequences. So how do we do this? So this is your x which y, and this is your x. Yeah. So y here fits in the homotopy push-out square. Yeah. Why is this true? This is true for a topological space level. If you see, this is not only a homotopy push-out. I mean, this fits in the homotopy push-out square. And how it happens? So if you look at for the topological space level, so if this is your topological space, let's say stop here. Now, if I take the co-fiber replacement here, that is your x cross y, x cross I. where the bottom portion is identified with x, h, y, right? And the top portion is identified with a point. Now this is your Cx. This is your essentially Cx, which y. Now Cx is contractible. That means that this is homotopic to your y logical spaces. So this fits in the homotopy push-out square, and that will give you a co-fiber sequence. And from this co-fiber sequence, you get to have this map ik of x to ik of x which y and ik of y, so on and so forth. Now we have to show that this guy is a split exact, and yeah, this is split exact because of there is a section. Yes, so y, the inclusion over here, y to x which y will give you the section over here, and that will give you the split exact sequence over here. Yep. So product and co-product coincide for spectra. And I will end this by giving you the model structure of spectra. So recall how we give to a model structure in topological spaces. Your co-fibrations, let's start with the fibration. Yeah, let's start with the fibration. Your fibrations were your serif fibration. Your weak equivalences were your weak homotopy equivalence. And your co-fibrations were basically identified with the left lifting property with respect to trivial fibrations, and that turned out to be for that we have found a generating set or I cells for n greater than equals to 0 and take the cofibrant generation. Right? I mentioned most of the categories we will care about, model categories we will care about are all co-fibrily generated. So is spectra. So for spectra as well, let's start with your fibrations first. Oh, spectra. Your fibrations are your cell fibration, level-wise cell fibrations. Such that it commutes, I mean, it definitely commutes. These squares are homotopy pullback square. Your, sorry about that. Your weak equivalences are your stable homotopy equivalence. And your co-fibrations. Here also I can give you a generating set, and the generating set is this. Your I cells are your this guy. So what does this mean? That simply means you look at Sn minus 1 and take a suspension spectra. So Sn minus, this is your zeroth space, Sn plus 1. I will also explain the plus, what the plus is standing for. You take the suspension of Sn minus 1, keep taking it. This is your 1th level, this is your ith level, so on and so forth. What does this D mean? That this D means you have shifted to on the D side. Now to shift it, I need to start with something, right? I need to start with a base point. And this plus is adding the base point. That's all. That's literally all it means. So plus always mean a base point in topological spaces in general. So that means that this is your zeroth space now. And at the dth level now, I have the Sn minus 1. At the d plus 1th level, I have suspension of Sn minus 1, and so on and so forth. And this is going for d greater than equals to 0, n greater than equals to 0. Now, you use this as your generating cofibration set, and you will get all your cofibrations. And I think we are already a lot past our time, so this is a good point to stop. So let's stop the recording here.
Thanks for your talk.
Oh, I'm sorry about that. It should have been a little bit more smoother.
By the way, who will talk on Friday?
Uh,
Next
I'm
week.
going to talk. I'm going to talk.
Yeah. Yeah.
So just I mentioned, I'll finish it within several sentences, that there is actually a delooping construction, which is related, which is like the other side of the conloop construction. So you first have to define it on simplicial groups, but extend it within the well, using infinity category. So basically enlarge the defining category to be infinity groupoid. So you do have a de-looping construction for spaces.
Okay.
Can I jump in here quickly? I have to go.
Yeah, go ahead.
It's not true that every space is equivalent to a loop space. The reason is that a loop space is an H space. There's a composition law. You can compose loops, right?
Yeah. It's not.
So it's absolutely impossible in general to say that a space is equivalent to the loops of another space. That's not true. In fact, the whole theory of operads is built around that observation, that to be a loop space, you have to have a composition law. And if you're a double loop space, that composition law is homotopy commutative.
Yep.
Now, what May and Bardman and Vogt observed is that to have an infinite loop space structure, so you want it to be a loop of a loop of a loop of a loop, it has to have all kinds of coherent, well, what? Products. It has to have products with all kinds of coherence. And what they did is they formalized that in the language of operads. You see, to be a loop space, you have to be an H space.
Yeah.
And most spaces are not H spaces. That's just not true.
I'm not saying that, actually. I'm saying there is a D-loop construction. I'm not saying every space is equivalent to a loop space.
Oh, sure. There are D-loopings in some sense, but it's just not true that every space is equivalent. You can't just say it's the loops of the suspension, for example. It's not the loops of anything.
No, it's not. It's quite true. So I'm saying there is a D-loop construction. I'm not saying every space. That's certainly not true. That's certainly not true.
Right. So in any case, I just want to go quick. I have to go quickly. The whole philosophy of operads is that you have these composition laws, and these composition laws are encoded in various coherence. It's not only a composition law, it's homotopy commutative. The commutativity has constraints among it, and the higher constraints. And so they encoded all this, I said, in the language of operads, okay? Now, I will say that it's later on, Graham-Siegel came along with a much, much more elegant construction called gamma spaces.
I did mention this.
Yeah. Now, gamma spaces are very, very simple objects to define. They're not much more complicated than simplicial spaces. They're almost on the same level of difficulty. And what Graham-Siegel observed is that these gamma spaces produce they produce spectra. In fact, you can prove they produce all connective, whatever that means. All connective spectra come from gamma space. It's a Seal theorem. Now, so these are called infinite loop space machines. So it's a very non-trivial business to actually manufacture a spectrum. That's not a trivial business at all. And I also point out these things, you could create sheaves of spectra, you could sheafify this idea, et cetera, et cetera, et cetera. Okay, well, anyway, I want to thank Krishnendu for giving a nice talk, and I'm sorry, but I have to run now. Okay, bye-bye.